Today's first question is going to be a science question. This has to do with black versus white t-shirts, you could say. When I wear a black or dark colored t-shirt on a sunny day, it seems to feel hotter than if I wear a light colored or white shirt. What is it about the color of the shirt that makes it hotter or cooler in the sun?
Okay, yeah, so this is a question that sort of deals with how light works and what light is, and it's sort of an interesting one. So the easy answer is that your black shirt is absorbing all of the wavelengths of light. And so let's assume that you are standing outside on a sunny day. The light coming down from the sun, I think we'd mostly agree it's a whitish, maybe yellowish light. And all of that light hitting your shirt is going to be absorbed. And when all light is absorbed by an object, that object appears black. And this sort of gets to the idea that when we see something, what we're actually seeing is the light reflected off of that thing. So if you're looking at an object and it's black, there's no light being reflected back to you. If you're looking at an object and it's white, then all of the light hitting that object is being reflected back at you. And then within that, you have different colors. So for example, if we think about, so first of all, let's think about a rainbow. So a rainbow is a division of white light. It's something that happens naturally when light is prismatized through something like raindrops. So you get this white light divided into Roy Jabiv, right? Red through violet, and all the colors that we're able to see. Then you look at something like a tree. Let's say the leaves of a tree reflect green light, and that's why leaves appear green to us. But then all the other colors, red light and blue light, for example, are absorbed by the tree. And in the case of the tree and the leaves of the tree, that's really beneficial because the light being absorbed, light is made up of small packets of energy that we refer to as photons. Those light packets, those photons, in your black shirt, they were just energizing the molecules of your black shirt and making you hot. But in the leaves of the tree, they're actually providing energy that moves electrons around, it creates the energy in the leaf for the leaf to then synthesize sugar, which is its food. It's the key to photosynthesis, is the fact that some of that light is absorbed. So anyways, in that black t-shirt, light is being absorbed, all the different wavelengths of light. It's not reflecting anything back. We see it as black. And all the light that's being absorbed is knocking the molecules of that t-shirt around and sort of speeding up their vibrations. All molecules have a natural vibration to them, which we think of as heat. But in the case of the t-shirt, the fibers, the molecules of the fibers are being knocked around, vibrating faster, and you would feel that as heat if you were outside. Just as one last thing, if we could jump to my screen, it's kind of a cool website that you can check out if you're into it. It's just an interactive optics website, or you can type in color model mixing synthesis if you wanted to check this out. But it's basically a thing that lets you take 3 colors of light. We generally divide light into red, green, and blue light. Of course, there are other colors that we see, but it's an easy way to think about light. And so what you can do with this website is you can shine something like red light down, and then you can see what would happen if you mixed it with green light. And one of the things you'll notice, besides the fact that you're getting yellow, and if you're an art student, you might say, well, I definitely don't get yellow when I mix green paint and red paint. And how color mixing works is a little bit more than I'm going to get into right now. But at least one thing that we can see is the color between the red and the green is lighter than the red or the green. And indeed, if we were to bump all these up to 100, the cross-section of the 3 of them should create a white space for us. Again, because when all the wavelengths of light are together and they're reflected back to us, we see that as white. So that was a lot of extra information. Hopefully it was useful.